After my short presentation, we will then start with Christoph Heinrich. He's a leading expert from Siemens AG, and he's working exactly on the convergence of simulations and AI, and basically creating these digital twins that are necessary to bridge this gap. And so with no further ado, I would like also to welcome Christoph Heinrich to the stage for his first presentation. And so I will just hand over, and if you have any questions, the people here in the audience, you can then come to the microphones, or if you are joining online, you can also ask questions there, and we will then answer them after his presentation. So thank you very much. It's your stage.
Thank you. Thanks for the introductory words. Thanks for the invitation of being here. And thanks to you, especially in this very challenging time slot just after lunch, to attend this session. I would like to give you some insights into simulation technologies. That's the focus, how they can bridge real and digital worlds, and then also help to enable physical AI. So there is a lot in the press for a good reason, because a lot of investments are done in physical AI, not only in the American tech world, but also in Europe, also in the automation business, where also we as Siemens play an important role. On the other hand, we see such movies. I just found 2 weeks ago, America's Got Talent. We see humanoids. They can dance with a human in perfection. And we may come to the conclusion that everything is solved already, that they can now take over the shop floor and do tasks that humans are doing or that machines are doing. But if we come to physical or to requirements from industry, then the question arises, okay, what's happening if objects are misaligned? Yeah? On the shop floor, but also here on stage, if there's something lying on the floor, if humanoids are a bit differently placed, or the human dancer makes a completely unexpected move, what's happening then? Also, when conditions are changing, like lightings or anything else, or in general, if there's some uncertainty happening, can these systems react in a safe way and in a precise way? And of course, in an industrial setup, we need to repeat tasks thousands and thousands of times. And does that work with the same precision here as well? Now, let's come back to, let's say, today's perspective on the shop floor in manufacturing. In the very left picture, you see what works very well, which is a process done by industrial robots. They do predefined tasks with high precision. They do it fast, with a high volume, and they act in a safe environment. But they're not really flexible in what they're doing. So if, for example, humans come into play, or if tasks are changing, they need to adapt to situations, then we need more flexibility, and we need to combine robotics and AI. And that's where we are in at the moment. That's the middle picture. And of course, we are also thinking about humanoids, because they are designed to do tasks in a human environment. But from an industrial perspective, they need to do tasks that make sense, that increase productivity, that enhance, or that they follow safety and precision requirements. We are not yet there, but we're thinking also in the future what they could do. So now, what is physical AI, and what is the connection to simulation? So physical AI is defined as a method that brings intelligence beyond the screen, that makes machines see, understand, interact with the surroundings. And there's another term which is called physics AI. So it's only 1 or 2 letters different, but the question is it fundamentally different? yes, it is, because physics AI is an AI trained on physics principles. You can think of the behavior of a fluid, which is then called computational fluid dynamics, or the behavior of structures. It can be used to model parts under loads in a fluid or the fluid itself to predict how it behaves in the future. But there is a connection. That's where simulation comes into play. So to build physical AI, we need physics-based simulation to end up in an accuracy that is acceptable from an industrial standpoint. And it also appears in world models that simulate realistic physical environments. And there's one problem. Here, there's an imitation pipeline depicted. So how does that work if we want to train a robot? You collect real-time data. You basically show the robot what to do, maybe via teleoperation. But this doesn't scale. Or you have many, many people that do it, then it scales. But usually, you would employ simulation that mimics or that is based on the collected real-time data and is scaled. So, for example, you do 10 teleoperated data collections and 1,000 simulations, and you deploy it afterwards then to the real system. But here is a problem, because you train in the simulation world and you deploy it again to the real world. And there's, in this sim to real transfer, it's called, there's a gap. And to bridge this gap, this is one of the long-standing challenges in robotics, to go a bit more into detail. So as I said before, you train in a simulation space. This is the green circle. But you deploy it then again to reality. That is the blue circle. So the best would be that they coincide, but this is usually not the case. So they intersect. In this intersection, the deployment is good, is ideal. So the idea is, how can we bring those two circles together? And here, simulation comes into play. There are methodologies, I will go into detail in a bit, like simulation enhancement or real-world data integration that help to reduce or close the sim-to-real gap. You could also think of, okay, I simulate and simulate, I collect just more data, and then at some point my model would be good. But this is not really efficient and makes your model not lightweight anymore, and you run into the situation that you might extend the green circle to the red side where it has no use, right? So how to bridge now this sim to real gap? Already told you, simulation enhancement is one thing, so it means that we use high-fidelity simulation. It's not just rigid bodies that collide, but more, and I will show you what I mean with that. And on the other hand, that we integrate real-world data to make such simulations more accurate. This is the second part. Now it's appearing. Here also methods like system identification come into play. I will explain also later. And of course, one thing is also about policy robustness. That means if you have an action model, that you have a control system that is resilient to those changes between the real world and the simulated world. All right, but this is not part of this presentation because simulation is mainly existing in the first two of them. So what do I mean with simulation enhancement? So if we again look at the imitation pipeline curve, so this is basically the middle part. We're now in the simulation world, and we have high-fidelity simulation, and we want to scale it down, create thousands of simulation in a fast manner. In other domains, like in product development, we already use for decades 3D simulation, physics-based simulation that are based on physics principles, on physics laws that are given by nature, right? And you can do a CFD simulation, as in the top picture with the jet. That's admittedly that's a marketing movie, yeah, but the result is the same. You optimize, for example, the shape of a wing, or in the bottom video there was a turbine, was a crash simulation where you do this virtually with high precision. Of course, also with high effort. That's what I need to admit. But you can use those simulation methods also for training to create the synthetic data. Means more accurate simulation to end up with a higher success rate in deployment, that the robot does with a higher probability the right thing. Another thing is, what I would like to mention is that physics-based simulation can also be used, and this is really powerful, to validate AI algorithms and also physical AI algorithms. Because it's physics-based, we can extrapolate, and it still fulfills the physical laws. That means we can create test scenarios that is not part of the training data in action models, and maybe for very rare cases where you also do not have real-time or real data. Whereas the validation part, you don't need real-time capable simulation. For the training, of course, you need fast simulation, and what you see on the left, it can consume hours, and depending on the simulation, even more. It can consume days. But I can show you now one methodology to speed it up, where physics AI is used. There's also a tool from Siemens, by the way, that is called Physics AI, which basically takes simulation data that was created in the classical way, here based on a robotic hand. A PhD in my team is developing and simulating. The colors are indicating the mechanical stresses. That means if you exceed a certain limit, then the fingers would break, or the part that you grab would break. And if you have different designs, different finger designs, you do the simulation, and with this you can then train a machine learning model. And if you then want to simulate a different design and kind of scale and create synthetic data, you can use this model by just providing a CAD model, because it's a geometric deep learning based method. And you can get then, for your new design, you can get an answer or a simulation in only a few seconds. So this is one methodology, and here is also a video I would like to show. What we also did is we built a whole pipeline. First, here it's also imitation learning that we did it also in the virtual space, show the robot what to do. In this case, we then also used NVIDIA Isaac Lab pipeline. We scaled it to many different scenarios, different variations, and in the very end deployed it. And here we also used the first time also deformable objects in the training data. And in this pipeline, we can also extend it with other solvers, with other simulation, or more physics-based and more accurate high-fidelity simulation. So this is one thing. Another one that I would like to mention is to integrate real-world data. Again, in an industrial setup, we cannot accept success rate in action models of 70 or 75%. It must be much higher than that. And here also we think that we need to use real-world data and infuse physics knowledge into so-called world models. Now it gets a bit more technical. So we are now in the last part of this pipeline. So we are in the deployment. That means we get real-time data in the real world, and we make use of it. And now here is a high-level architecture how this may look like. So there's a state. These are the green boxes that are describing the current state of the robot, of its environment. We have a perception module on top of it that's having observations that can be coming from a camera, can also be coming from any other sensor. Yeah, it's not limited to that. And we have a dynamics module, which basically propagates this state from one time step to another, maybe from 1 second to 2 seconds, and have then here a kind of time series that is created. And at the same time, of course, we have an action model, which is then also giving input to this dynamics module, or the control module giving actions to this dynamics module. And with this, we can propagate a state from one time step to another. That reminds us a bit on recurrent neural networks, taking old time steps into account, the previous knowledge into account. And this is currently our research focus. So here, some questions are arising. How do we optimally describe such a state? How do we describe such a dynamics module and also infuse physics into it based on physical equations, other methods, simulation, and also what is optimal conditioning, for example. So what information from the perception do we also need to have an optimal dynamics module? So there are many methods already existing that are largely not used in robotics, so there's something really to leverage here in, for example, using fast solvers, using a model order reduction. This is basically a technology that is there already in the simulation world for many years, which makes it possible to simulate fast, but still accurate enough if you know what your target actually is. Of course, there's no free lunch, but you can tailor your methods to be here also very precise in a latent space. I would like to give you one example that fits into this. This is what we have done already some years ago. What you see is an industrial robot, a classical robot. If we go back to the second slide, it's maybe on the very left, at least a device on the very left that we know from car industry. And we wanted to make them mill with high precision. The problem is here that such an industrial robot is usually is flexible, and the problem is that sometimes it's then even more flexible than the part that should be milled. So it can happen if you want to mill a straight line with such an industrial robot, you would rather create an arc than a straight line, because the part that you're milling is more rigid than the robot itself. So what we did here is that we employed a so-called executable digital twin. That means it's a fast simulation model that is deployed on edge, and it has a model of the process inside, of the milling process. With the help of this model, you can then estimate forces on the milling head and also estimate which measures should be taken. That means that you basically create counter torques in the joints of the robots to compensate this deviation. And what we achieved with this, so you see here in the back, or on the screen, it's only in my back, you see the part from top that was just milled, and the contour. And the colors, they are indicating the deviations from the actual planned milling paths. So blue and red mean that we have deviations up to 1 millimeter. This is usually not acceptable in an industrial environment, so the accuracy is not good enough. And if we now employ this method, we can go down to 0.1 millimeter, so a increase in accuracy by a factor of 10. And 0.1 millimeter is something that is acceptable for many parts already. So this is an example where we used a world model, namely that of the milling process of the workpiece and the robot. We infused real-time data, which was coming from the control system. And we used a physics-based model contained in this executable digital twin that was also run in real time next to the movement of the robot. So this is my last example, and I would like to summarize at a point. So what we have seen is that the sim-to-real gap is a key limitation for physical AI. Simulation is one means to enable that. What we have seen today is simulation enhancement. It means simulation with higher fidelity that has physics inside that is used, for example, in product development and accelerated. And we integrate real-world data and use physics-based world models. These are the two things that I wanted to show you today. And I would like to stress one thing, that physics-based simulation is essential if we want to validate and verify AI and physical AI algorithms to make them safe, especially in applications where this is of high importance, to make them also accurate, because this is a key requirement in industry and for sure also in other domains. And so that means in an industrial deployment, we need high safety, high accuracy, and I would like to stress as my last picture also that we as Siemens, we are part in many organizations worldwide, but also in Europe. For example, in the Big Data Value Association, which is a part of the Euro HPC that Dennis mentioned at the very beginning, an industrial-driven private member of Euro HPC, and also driving forward, on the one hand, the computing infrastructure. Then we need industrial-grade data. That is what is achieved in initiatives and projects like Catena-X or Manufacturing-X, and then also apply them in applications, in industrial applications and with industrial grade. With this, I would like to close. Thanks a lot for your attention, and I'm happy to answer any questions. Thank you very much.
Yeah. Thank you, Christoph. So are there any questions here in the audience? So if yes, please stand up to the microphone. Yes? Okay.
Yes, the question is, how do you integrate imaging data and physics in a single model?
So integrate physics data and...
Because you have physics simulations or mathematical equation, and then you have imaging data. How do you bring that together in a single neural network?
I mean, we are using pipelines that are existing. This is for sure also a field of research, but you can basically, with physics-based simulation, also create, for example, image data as well, and then you are already with again in the same space. Does that answer the question, or? Yeah,
to some extent, yeah. So,
okay.
But there are models where you could merge equations within the neural networks. So you're not doing that. So rather you use physics to generate imaging data and then train it normal.
So this is one possibility, but we're looking also in other domains that we have multi-modal data or different data from images, but also from physics, or also to identify physics in images, right?
Okay, thank you. I've seen a question online which I think fits also as a follow-up question to your one. Do you use physics-informed deformable Gaussian splatting in your lab and projects?
Physics-informed?
Physics-informed deformable Gaussian splatting.
Okay.
So it's going technical now.
Technical, okay. So what you have seen in this video, at least with the two-arm robots, here we used deformable objects at the first time, and but the Gaussian splatting, I really need to I need to look it up if this is part of our work.
Okay, so I have also some questions. So you have said that basically simulations are the building block of everything, and I assume you're looking quite a lot for accuracy. Now we are seeing the trends going from CPU to GPUs, and we also see the trend in GPUs basically removing the floating point 64 operations. How do you see that, how this would influence your work with respect to physics-based simulations?
That's a good question, and of course, years ago, to create such physics-based simulation, it was key to have CPU power and RAM, a lot of memory. But solvers, they are now using GPUs as well, so this is what we have just shown also, for example, with SimCenter Star CCM+, where you could accelerate, for example, computational fluid dynamics simulation, like with the airplane that was in the movie, and accelerate it just by using a GPU, and of course the solver needs to be adapted to the GPU. But here an acceleration alone was done by a factor of 30. And then if you then put on top further numerical algorithms to make, you can even make them faster in this so-called model order reduction schemes. So GPUs have also reached the simulation world, the physics-based simulation world, and first results also have shown that a factor of 30, depending on the application, is reachable, which is really great.
And we are at an HPC conference. Can you also quickly say a little bit how your compute infrastructure looks right now and what you envision also for the future, how much compute you would need, and if something like the AI factories would be helpful for that?
Yeah, so I cannot put it really in numbers, but as I said before, now we're going from CPU to GPU. We need memories. This is essential for simulation, and we're using at the moment clusters, but we are maybe it is not so we don't have the requirements for training large language models. The data, so we are in reduced spaces, so maybe not at this extent. But simulation per se, it really depends on the application of how complex it is, and also the compute time and the compute requirement. It's a difference if you use you want to simulate a fully blown aircraft or just something which is much smaller with less part and less safety. And it also depends on your, as you were mentioning, the accuracy. It really depends on the application. If it's safety relevant, you have other requirements than in other applications where you can cope with some reduced accuracy.
Okay, then thank you very much again, Christoph.
Thank you.